Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into the distributed scheduler, the system that runs background jobs reliably across a fleet of machines, even when nodes crash, networks hiccup, or clocks drift. We'll cover cron expressions, lease-based ownership, worker pools, retries, dead letter queues, and at least once execution. Whether you're preparing for a senior engineering interview or building a cron replacement at scale, this one is for you. Let's get into it. Welcome to Cloud Wizard. In this video, we are doing a complete deep dive into the distributed scheduler, the system that triggers background jobs reliably across a fleet of machines, even when nodes crash, networks hiccup, or clocks drift. If you have ever wondered how platforms like AWS EventBridge, Google Cloud Scheduler, Azure Logic Apps, or internal job orchestrators run millions of recurring tasks without double execution or missed runs, this video is for you. We will walk through the functional requirements, non-functional requirements, system architecture, end-to-end user journey, core models, low-level design, and the trade-offs that come up in a senior system design interview. Whether you are preparing for a FANG interview or building a cron replacement, let's get into it. Here is the core problem. Most products start with a single server running cron jobs. It works fine at first, but as the business grows, the cracks appear. If that machine is down when a job is due, the job is simply missed. If two instances are running for high availability, the same job may execute twice and corrupt data or charge a customer twice. If a job takes longer than expected, overlapping runs can overwhelm the database. If a job fails, there is no centralized retry queue, no dead letter archive, and no visibility into what went wrong. There is no horizontal scaling, no leader election, and no way to schedule one-off jobs dynamically. The business needs a distributed scheduler, a service that accepts job definitions, tracks when they are due, assigns them to workers safely, and guarantees progress even when the system is partially broken. Let's walk through the functional requirements. First, the scheduler must accept job definitions, including recurring schedules using cron expressions, fixed intervals, and one-off execution times. Second, it must trigger jobs reliably at their due time, accounting for clock skew and scheduling latency. Third, it must guarantee at least once execution, meaning a scheduled job is eventually run even if a worker crashes mid-task. Fourth, it must prevent duplicate execution when multiple workers or scheduler instances are active, typically using leases or locks. Fifth, it must support retries with exponential backoff, jitter, and a dead letter queue for permanently failing jobs. Sixth, it must provide visibility through job status, execution history, next run predictions, and alerting. These 6 capabilities separate a toy cron from a production scheduler. Now the non-functional requirements. The scheduler must be highly available, because background jobs often drive critical business workflows like billing, reports, and reminders. It must be fault-tolerant. Worker crashes, scheduler restarts, and network partitions should not cause lost or duplicate jobs. It must scale horizontally, supporting millions of scheduled jobs and thousands of workers without a single bottleneck. It must offer low scheduling latency, so jobs start close to their intended time, even under load. It must be durable. Job definitions and execution state must survive storage failures. It must be observable with metrics on schedule lag, execution success, retries, and lease contention. And it must be safe, with authentication, authorization, and isolation so one tenant cannot block another's jobs. Here is the high-level system architecture. On the left, clients interact with the scheduler through an API and a web console to create, update, and monitor jobs. The API writes job definitions into a durable job store, typically a relational database with strong consistency. A scheduler leader, or a set of scheduler partitions, periodically scans the job store for jobs that are due. When a job is due, the scheduler claims a lease for it and places an execution task into a distributed queue. Worker instances pull the queue, execute the job, and report the result. A lease manager tracks which worker owns each execution, and heartbeats extend the lease while the worker is alive. A dead letter queue stores jobs that exhaust retries, and an alerting service notifies operators when jobs fail or fall behind. A metrics and dashboard layer surfaces schedule lag, throughput, and worker health. The key metrics to memorize: cold schedule lag, the delay between the intended trigger time and the actual start time. On-time execution rate, the percentage of jobs that start within an acceptable window. Duplicate execution rate, the percentage of jobs that ran more than once, which should be extremely low. Failure and retry rates, which reveal how often jobs fail and how often they recover. Dead letter queue depth, which tells you how many jobs are permanently stuck. Worker utilization and queue depth, which guide autoscaling decisions. Lease expiry rate, which indicates how often workers are crashing or losing connectivity. And execution duration, which helps you detect slow jobs and set appropriate timeouts. These metrics are the operational health of the scheduler. Let's trace the end-to-end user journey. A platform engineer at a SaaS company needs to generate daily billing reports for thousands of customers. She opens the scheduler console and creates a job named Daily Billing Report with a cron expression of 0:30 every day, a max retry count of 3, and a timeout of 10 minutes. The scheduler stores the job, computes the next runtime, and waits. At the scheduled time, the scheduler leader claims a lease and queues the task, and a worker picks it up. The worker runs the report, sends the results to S3, and marks the job as succeeded. On the dashboard, the engineer sees a green status, the runtime, and the next scheduled run. One day a downstream API is down. The worker fails, retries after a minute, fails again, and finally succeeds on the third attempt. The engineer sees the retry history and confirms the report was generated without duplicates. The core models and algorithms. The cron parser translates cron expressions into a sequence of next run timestamps, handling time zones and daylight saving time carefully. The job store persists job definitions, schedules, and status with strong consistency for lease operations. The lease table maps each in-flight execution to a worker, an expiration timestamp, and a unique token, preventing concurrent execution. The task queue holds ready executions waiting for workers, often ordered by priority and scheduled time. Worker pools use long polling or push subscriptions to receive tasks, and they send heartbeats to renew leases. The retry policy defines backoff intervals, jitter, and maximum attempts before moving a job to the dead letter queue. The idempotency key lets workers rerun the same logical job safely without side effects. At least once delivery is the default guarantee. Exactly once requires idempotent workers plus a strong lease. The key trade-off is latency versus safety. Aggressive leasing triggers jobs fast but may duplicate if heartbeats are lost, while conservative leasing reduces duplicates but adds delay. Now the low-level design deep dive. The scheduler service is split into a control plane and a data plane. The control plane accepts API calls and writes to the job store. The data plane is a set of scheduler partitions, each responsible for a shard of jobs. A partition scans its shard for due jobs, acquires a lease by inserting or updating a row in the lease table with a conditional write, and publishes a task to the queue. Workers pull the queue with prefetch limits, receive a task, and call the lease manager to verify the lease is still valid. While running, the worker heartbeats at a fraction of the lease duration to extend it. On success, the worker records the result and releases the lease. On failure, the scheduler computes the next retry time using exponential backoff and jitter, then re-enqueues the task or moves it to the dead letter queue after the max retry count. The dashboard reads the job store and execution history to show status, latency, and retry traces. All writes to the lease and result tables use row-level locking or conditional updates to avoid race conditions. Key takeaways for your interview. First, a distributed scheduler is fundamentally a state machine around lease ownership, so always start with the job store and lease table. Second, separate scheduling from execution. The scheduler decides what is due, and workers do the actual work. Third, use leases with heartbeats and unique tokens to prevent double execution. But remember that true exactly once also requires idempotent workers. Fourth, at least once execution with retries and a dead letter queue is the practical baseline for production systems. Fifth, Scalability comes from partitioning the job store and sharding scheduler leadership, plus auto-scaling worker pools based on queue depth. Sixth, observability matters. Schedule lag, duplicate rate, and DLQ depth are the metrics interviewers expect you to mention. If you can walk through this system with these 6 points, you will signal strong senior-level design thinking. That's it for the distributed scheduler. If this helped, like and subscribe, and I'll see you in the next one at Cloud Wizard. And that's a wrap on the distributed scheduler. We covered the full picture, from job definitions and cron parsing, through lease tables, worker pipelines, retries, dead letter queues, and the low-level design that keeps jobs running once and only once. If this video helped you, please hit that subscribe button and the bell icon so you never miss a new system design video. Drop your questions in the comments below. I read every single one. See you in the next one at Cloud Wizard.